We are now going to continue with our lessons on joint distributions and talk about independence of random variables. We're going to start with discrete distributions, and I want to start with a fact that if we let x and y be discrete random variables with joint probability mass function p of xy and marginal probability mass functions p sub x and p sub y, then x and y are independent if and only if the probabilities multiply, meaning that p of jk is equal to the marginal probability of x evaluated at j times the marginal probability of y evaluated at k for all possible values jk of x and y. This is easiest to understand if we look at an example. We're going to let x and y be the outcomes from two tetrahedral dice, each numbered 1 through 4. So the first question is, are x1 and x2 independent? Well, we need to look at the probability that x1 equals a particular number, we'll call that j, and x2 equals a particular number, we'll call that k. Now, because there are two dice, numbered 1 through 4, that means there are 16 total outcomes for the ordered pairs j, k, and each occur with probability 1/16 because they're equally likely. But we notice that 1/16 is equal to 1/4 the probability of rolling one of the values for x1 and times 1/4 the probability of rolling one of the values for x2. And so this is the marginal probability of x1 evaluated at j times the marginal probability of x2 evaluated at k. So therefore, yes, x1 and x2 are independent, as we already knew from our work with dice. But in our previous lesson, we also looked at two random variables, y1 and y2, where y1 was the minimum of the two dice, and y2 was the absolute value of the difference of the two dice. And we can ask ourselves, are these random variables independent? I've provided you a chart of the joint probability mass function for y1 and y2 so that can help us determine whether the probabilities and the random variables are independent. So I want to look particularly at the first column of this chart, the probability that y1 equals a number k and that y2 equals 0. And we'll notice that these probabilities are always 1/16. These are the probabilities where x1 and x2, the two dice, are equal, and we're particularly looking at when both dice are 1, 2, 3, or 4. Each of those events happens with probability 1/16. Now, what is the probability that y1 equals k times the probability that y2 equals 0? Well, that's equal to the probability that y1 equals k. And then the probability that y2 is 0, we can see from the sum of the first column, is 1/4. But something that we should notice is that the probability that y1 equals k, which is given by the row sums in green, that probability is never 1/4. And so that shows that these probabilities do not multiply together to get 1/16. So let's ask another question. Are x1, the independent, or the outcome from the first die, and s, the sum of the two die, independent? Well, let's look at a particular outcome. What is the probability that x1, the first die, equals 1, and the sum of the dice equals 8? Well, there's actually no outcomes where the first die equals 1 and the sum of the die are 8, because each of the dice is only numbered 1 through 4. So the probability of this occurring is 0. But the probability of x1 equaling 1 does exist, and that's equal to 1/4. And the probability that s equals 8, the sum of the two dice, is 8, does exist. That happens when both dice are 4, which happens with probability 1/16. And those two multiplied together is 1/64, which is of course not 0. So therefore x1 and s are not independent. And this is a trick that you can use when looking at whether two discrete random variables are independent. You can try to find events where the outcome of the first random variable occurs with probability not 0, and the outcome of the second random variable occurs with probability not 0, but the probability of both of them happening together is 0. So these were two examples where both random variables were not independent. Let's see if we can look at some examples where the random variables are independent. So let's look at an example where you repeatedly roll two dice until the sum or 7 over 11 appears. So n is going to be the number of rolls it takes to get a 7 or 11, and x will be the sum of the two dice on the final roll, either a 7 or 11. And we want to show that x and n are independent. Well, if we're going to roll the dice until a 7 or 11 appear, then n is a geometric random variable with parameter 8 out of 36. There are 6 outcomes where a 7 is the sum of the dice, and 2 outcomes where an 11 is the sum of the dice. So that makes a probability of 8 out of 36 for the sum to be 7 or 11. This tells us that the probability that n equals a particular number, the number of rolls is a particular number k, is equal to the probability of failure, 1 minus 8 out of 36, to the k minus 1. So k minus 1 failures times the probability of success, 8 out of 36. Now we're going to look at what the probabilities for x are. X only has 2 outcomes. The final roll, if we're going to keep rolling until a 7 or 11 appears, can only equal 7 or 11. Now the probability that x equals 7 is really the probability that x equals 7 given that the final roll x is 7 or 11. And that occurs 6 times out of 8 times, because a 7 can occur 6 different ways, and a 7 or 11 can occur 8 different ways. The probability x equals 11 is really the probability that x equals 11 given that x equals 7 or 11. And that occurs 2 times, because there's 2 ways to get an 11 out of the 8 ways of getting 7 or 11. Okay, now we ask ourselves, finally, what's the probability that n equals k and x equals 7? Well, for n to equal k and x equals 7, we need to have 28 out of 36 rolls to the k minus 1. So saying that we have to fail to get a 7 or 11, k minus 1 times. And then we need to finish with a 7, which occurs with probability 6 out of 36. Well, what does that equal? Another way to rewrite that is 28 out of 36 to the k minus 1 times 8 out of 36 times 6 out of 8. And you can see that is the probability that n equals k times the probability that x equals 7. So we'll do that again one more time for the probability that n equals k and x equals 11. Here we have, if we're going to roll repeatedly until 7 or 11 appears, then the probability of failure is 28 out of 36, and we're going to roll that k minus 1 times. But finally, we're going to have a success, but that success is going to be that we roll an 11. That happens with probability 2 out of 36. Now we can rewrite that as 28 out of 36 to the k minus 1 times 8 out of 36 times 2 out of 8. And that is the probability that n equals k times the probability that x equals 11. And so we have shown that for both values of x that can appear in this experiment, that the probability of n equals k times, and the probability x equals one of the values, 7 or 11, equals the product of the two probabilities. And so yes, n and x are independent. Let's do one final example. This is one where we take advantage of the fact that we know that we have independent random variables. So we're going to let x1 through xn be independent random variables where x is a geometric random variable with success probability p sub I. And we want to find the distribution of the minimum of x1, x2 through xn. And this is the number of trials required until the first success occurs amongst the n simultaneous experiments. So you can imagine that we perform the same experiment simultaneously n times, and we keep running that experiment over and over and over again until one of the n experiments has a success. And that is what y is describing. So we want to figure out what is the probability distribution for y, and a clever trick is to look at what is the probability that y is greater than some value k. Well, if y, the minimum of x1 through xn, has to be greater than some value k, then that's the probability that x1 has to be bigger than k, x2 has to be bigger than k, all the way down to xn has to be bigger than k. Because if one of these random variables was not bigger than k, then we would have ceased running the experiment. So this is actually, because these are independent random variables, the product of the n independent trials where we're looking at the probability that xi is greater than k, since each of the random variables has the same distribution. Okay, so what is the probability that x sub I is greater than k? Well, if x sub I is greater than k, that means that we must have failed k times to have a success. So that's 1 minus the probability of success to the kth power. Well, we can rewrite this as the product from I equals 1 to n of 1 minus p sub I, all to the kth power, since each of the 1 minus p sub i's are already to the kth power. Now we'd like to really be able to describe this distribution, so I'm also going to rewrite this one more time. This is going to be 1 minus the product from I equals 1 to n of 1 minus p sub I, all to the kth power. So here all I've done is essentially add and subtract 1. But you'll notice that now this probability distribution, or this probability, looks like 1 minus the probability of success to the kth power. So essentially, we can say that y is another geometric random variable where the success probability we're going to call r, and r is equal to 1 minus the product from I equals 1 to n of 1 minus p sub I So here, if we want to list out what the distribution is, the probability that y equals k, because it's a geometric random variable, that is the probability of failure, 1 minus r to the k minus 1 power times r.